Hello everyone, welcome to Stochastic Calculus for Finance 1. So now we're moving to chapter section 6.3, which deals with the fixed income derivatives. And in this first part, we're going to be focusing on forward prices and forward rates. So our goal in this session, first we're going to talk about the risk neutral pricing formula, but within the binomial asset model, and specifically in the binomial tree model that we have here. Then we're going to talk about forward contracts, and then forward interest rates, and then how to define them, how to compute them. So let's go. So first, when we're talking about risk neutral pricing, and suppose that we are in the binomial model for interest rates. We have an asset denoted Sn, and this asset Sn is the payoff really depends on interest rates. So this is kind of similar to what we have, among my first video when we're talking about the binomial asset model, where Sn there was a stock, right? But now we're talking about interest rates. So what we're saying here is a discounted asset price is a martingale under the risk neutral measure P tilde. And that means that we have this formula here. And this is very similar to what we had before when you were like with stocks. The only difference now is for the discounting. Instead of the discounting being outside of the expectation, the discounting is now inside, because now we're allowing interest rates to be stochastic actually. But it's the same thing when for pricing derivatives. What you need to do is look at the payoff, expected payoff, and then discount that to the present. And that's what all we have here. And this is something that we're going to use over and over and over again. So now let's talk really quickly about forward contracts. So here I'm just before we forget, I'm noting here what we found before, that the discounting asset price is a martingale under the risk neutral measure. And also we have this that we have seen within the definition for the zero coupon bonds. And if you want to remember what this means, is just if you have a zero coupon bond that pays maybe $1 at time M, if you want to find the price as of this time N, we can think about it this way. First you take this $1, you discount it to time 1, and to discount to time 1 you need to multiply it by dm, right? This is a discount factor. And then you take it here, and then you forward value it to time N. And to forward it to time N, you need to multiply by 1 over dn. That's one way of thinking about it. And since these are stochastic, you need to take the expectation, and we are within the risk neutral measure. So that's one way of thinking about it. Another way to think about it is basically at time dm, when you do this subtraction, at time dn is actually known. It's a constant. But we talked about this quite a bit in the video on zero coupon bonds. So I will stop there. So these are two things that we're noting here, just to make sure we don't forget them. So now let's talk about forward contract. A forward contract is an agreement to pay a specified price K at a given date M for an asset whose price at time M is SM. So we can look at this picture here to have a better idea what this means. So at time M, we're getting the asset whose value is SM, right? So we're getting that. And then in exchange, we're paying a fixed amount K. And if we're standing, let's say, at time 0, right? K is known. This is a constant, a fixed amount. But SM is stochastic. We don't know exactly. But we know for a fact that we're going to be paying K. And we're receiving this amount, whatever the asset price is at time M. And that is what that is like the idea of a forward contract. Then when we talk about M forward price, what we're talking about is the value of K, such that the value of this forward contract have no arbitrage value as of time N. So let's say we're standing at a given time, N can be 0 as well. We're standing at the given time. What is the value for this K, this constant, so that there is no arbitrage possible? And to do that, to compute that, we will show that The M for our price is given by this formula here. It's just basically Sn, the value of the asset as we know it today, divided by BNM. And I will show now how where this formula is coming from. So from the risk-neutral pricing, what we have is this equation here. And what this means is like we're saying it's 0 because we want to find the K such that this thing is 0. And this thing like SM is how much money we're getting at time M. K is how much money we're getting at time we're paying at time M. And then we take this and we discount it, right? We discount it by dn, and this needs to be equal to 0. So what we can do now is we can put this Sn inside here. We can take this is going to be this, right? And then we expand it for the K, that's going to be that. And then next step, we're just going to take this guy and move it on the other side, right? And now if you notice what you have here, SMDM became SNDN. And the reason is because that the discounted SM is a martingale under the risk-neutral measure. That's what we said. That is exactly what this equation is telling us. So we just simply replaced that here. And then next step, what we can do is look at this. This became this. Where is it coming from? Well, we know that B and M is equal to this expression here, right, as of time n. And then the expectation is of as of time n, and dn depends only on the first n minus 1 coin toss. So this dn is actually a constant, right? So we can take this dn out. So expected value as of time n of dm is nothing but dn multiplied by bn dm. That's all we have here. Nothing too mysterious there as well. And now it's a simple algebra really. This dn cancel out. We want the k, and that's all we have here. And this k is actually the 4-hour rate because it's the very specific k that makes the value of the contract equal to 0. That's why we have this here. Okay, so I think hopefully this is fairly straightforward. So now let's talk about like 4-hour interest rates. So 4-hour interest rates, and we denote this by F and M. This is the interest rate at time n one can lock for a loan from that date M to date M plus 1. What does this mean? Let's look again at our timeline. Let's say we're standing at time n, and we want to know, okay, we want to enter into a contract such that at time M, let's say we lending to someone $1. At time we're lending $1, and then at time M plus 1, we're going to, of course, getting back our $1, right? But on top of our $1, we're going to get some type of interest rate because we just lent you our cash. And this interest rate here is going to be this F and M that we're talking about, right? And this is the F and M that makes that this contract is fair, aka there is no arbitrage again. So we can price this actually, right? From the risk-neutral measure, risk-neutral pricing, we have this. So we take this, we take the cash flow that's occurring at time M, and then we need to discount it, right? Just discount it back. And then we take the cash flow that's occurring at time M plus 1, and then we need to discount it back as well, right? So at time M plus, we're getting this K plus this 1. That's where this 1 plus K is coming from. And this minus 1 is nothing but this minus 1 that we have at this time here. And since like we want this K such that this contract is fair, we're saying the initial value is equal to 0. And then we're going to try to find this K. So what we can do here is we can take the expectation. So this guy, this is expectation to n. So this is the first term that's just coming down here. And now this term with the minus is going to go on the other side of equality sign, right? And we have expected value as of time n of dm. Now, okay, So this expression is just again the same thing here. We're taking this dn out, right? And so technically we can say you have this dn time dn. And on this side also, it's kind of like the same expression, but here instead of m we have m plus 1. So here it's going to be n plus 1. And it is as of time n, we take this dn out as well, right? So you have bn plus 1 and then dn, and then naturally these two dn's are going to cancel out, and you're left with this relation. And then from here we can do some math. So this fm is nothing but the k, right? So when you solve for the k here, you first dividing both sides by bn plus 1, and then you divide by bn plus 1, right? And this one comes on the other side and becomes a minus 1. That's the expression that we have here. Very, very simply. And this is the 4 rates. So, well, actually, we can do some math if you want, but you will notice that actually the interest rates at time m that I can log for between time m and time m plus 1, just as a definition here, is nothing but rm. Why? Because rm is just the interest rates from time rm to rm plus 1. So, but then we can check that as well. If you replace this by m, and then using the definition of this bm, what it means, then you will find rm as well. Okay, so then from this expression here, it is sometimes useful to just look at it this way, right? It's just like this. These two are the same expression. If you just do some algebra, you will see that they are equivalent. And something interesting to know is that now if you have your tree as we had before, right? And on this tree, we have shown that you know how to compute the price of the zero coupon bonds, right? We then look at these 4 rates. This 4 rates is just basically, if I want to compute it, I will need to compute this guy on the tree. I will need to compute this guy on the tree. But we know how to do that from the video on pricing zero coupon bonds. So that means now we do know how to compute 4 rates as well on this tree model, which is pretty cool. So recap, we talked about the reasonable type pricing within the binomial model for interest rates. We talked about 4 contracts and how to price them. Then we talked about 4 interest rates also and how to find the 4 interest rates pricing. So thank you very much and see you in the next videos.